Request Professor Devashish Gangopadhyay, our HOD, to say a few words to inaugurate this one-day discussion meeting on random walks, and then we'll take over.
So welcome everybody to this one-day workshop on random walks. And the first speaker will be Professor Giuggioli, Professor Luca Giuggioli from the University of Bristol. He did his, he's from Milan originally, and he did his studies in Milan and New Mexico, and also at Princeton as a postdoctoral student. Subsequently, he joined Bristol. Now, the aim of we are, for the last few years, we are trying to highlight, the department tries to highlight the exciting new topics that have come forward in physics research, and one of them is obviously random walks, and also the quantum version of random walks, on which you will be hearing today in the later speeches. And Professor Luca is visiting us for some time, and I invite him to just begin this. Thank you.
What do you need? I think it's working. It's working, yes. Okay. Well, thank you very much for the introduction. Well, first, let me thank very much Shamik and the physics department for hosting me here, and all the various visits I had, across the globe. I've never been pampered as much as I've been pampered here, I have to say. So thank you so much. I mean, really. So this one, it doesn't matter if it's like this. So okay, so let me talk about this topic, and it's pretty much about random walks, and if you want, it's specific to a model, but I thought some of the interest here is to see application of random walks, and you'll see we live and analyze data with this kind of model. So you'll see it's quite, it can become very useful. So before I forget, let me thank over the years the various collaborators I've had. And so there are some students and colleagues, and where is it? Yeah, this one. Okay, so this one is the last student that has decided to work on it. He just started his PhD on, and I'll have some slides about it. Mainly, I'll tell you about some stuff that I've done with my former student, Alejandro Roberts. Actually, he was also doing a short postdoc after that with me. And also, you'll see something about another student, Jonathan Potts. Now he's an academic in the UK. So some other names probably, they don't deserve to be named because everybody knows them. But, so okay, so let me start. And yeah, no, I know, but why it's not working anymore? Just a sec. No, okay. Maybe the back. Oh, it does. It does. Okay, so I'll tell you about, there will be a little bit of a biological introduction. So I think it's not working properly. And then I'll show you this model. It's a collective movement model. It means there are lots of particles, which are the animals that move around and interact. And so that's how you represent these formational territories. And then in principle, okay, so I think I'm going to abandon this. I just do that. No, don't worry. So I just press it. So, and then you'll see that in order to analyze data, if you have this big simulation, it may not be that convenient. So you will see I'll discuss about an analytic approximation of the model and how we have used that to analyze data of fox movement. Actually, it's a fox movement in Bristol, so precisely the city where. And there is a colleague there which has been working on foxes for over 30 years. So it's a tremendous data set. So we actually were lucky enough to use them. So in the city? In the city, yeah. So let me start with this biological introduction. And what is animal territoriality? Well, so it's a behavior that makes animals exclude others for certain region of space. So you can imagine, now this is my territory. And how do you actually manage to do that? There are different signals that you can use. And so there could be, auditory, visual, or olfactory. These are the typical things that you can think of. In fact, I have 3 images that represent, a baboon hooting. So that's your auditory signal. So whoever is nearby that could hear that will know, oh, that belongs to someone else. Then you can have a visual contest, like the two cats there, and so they have to be in very close proximity for that to happen. And then the fox, which is, this is the red fox, which you see, will analyze data. So then you don't have to be there, because you just deposit scent, and then you go. And then you only, after sometimes you have to go back. So that's olfactory cues. So you just smell it. And so, your dogs is very territorial, as you probably, if you have a dog, and you'll see that. That's similar behavior. Now, this is the definition in terms of biology. So what is it actually in terms of, from the physics perspective, is a form of collective movement. So collective movement, if you have never heard about it, it's about a set of objects or interacting objects that move in space and do something as they meet or they get close to each other, and then you have your interaction. So it's a big area of statistical physics, if you want, about collective movement. So, but what happens is that as you have this animal, and we'll go into the details, the territory form keep changing shape because of the interaction, the movement of the individual that generate them. So that's what this territory is. I'll be more precise defining what a territory is. So
what is conspecific?
Conspecific is the same species individual, because you can have actually territorial engagement between different species. So I'm not going to deal about that. So we'll talk about the case of olfactory cues, so which means there will be an animal that deposits scent and others that react finding the foreign scent. So now, as a broad overview, so what are the questions in animal territorial studies? In biology, it's what you find. You can distinguish in the why, the how, and when and where, as usual. So the why questions is about why animals are territorial. And of course, they have to defend something. It could be also some social status, and typically it's resources. No? So that's the why question. How is the one we are very much interested in. It is what are the actual mechanisms for which this territory can emerge, and how you defend your territory, how they are maintained. So this is the part that we'll be very much interested. The when and where, so whenever you have some sort of spatial-temporal structure, you need a ruler to measure things. And so, and these are the sort of questions that people are interested in. These are often called home range questions. And there is a large literature on measuring this territorial behavior in biology. I'll not touch any of this. So just to summarize, so we have this sort of optimality question. These are behavioral biology questions, and which I'm not going to touch upon. So these are the ones we touch upon, the animal interaction question. And these are the home range questions. I'll define what a home range, different from a territory, is in a slide, just for your knowledge. But mainly we'll focus on the interaction question. So that's what we'll go about. So if you have a scent marking species, remember, you have to think about a fox. They move about, deposit scent, and then goes off, and then only after some time to return. So you have to define the fundamental aspect of this collective movement is how they interact. Well, of course, how also they move, because it's a statistical movement. But the key part is how they interact. So if you have a scent marking species that you're trying to model, so they have to deposit a scent. So you have a scent marking process. And then you have what is called the territorial defense, to be more specific. And then you have the reaction as you find a foreign scent. So it's conspecific, so same species avoidance. So you find because animals have great ability of recognizing lots of things about the scent of different individuals. So there are lots of information, but one important thing is that if you don't want to die and get into a fight for which both individuals will be crippled for the rest of their life, they better avoid each other. So once they find it, you retreat. So that's a conspecific avoidance. So in fact, if you want to be more specific, you have a scent deposition, which is a process wherever you go, you leave a mark. And then the territorial defense is made up of two parts. So the scent is a short-term cue, because after some times, that scent, you can think about you're in the environment, it evaporates. Or if you don't want to think about evaporation, there is always a decision in the animal when he finds a foreign scent. He detects something, and then he can decide, oh, this is informative or uninformative. So it could be old or not old. So it is still there. And so that's a short-term cue. And so therefore, if you want to defend that location, you have to go back and renew it. And so notice that I put also broadcast signal, because remember, this is a really broadcast signal, because although it's local, whoever goes there within the time for which the scent is still active, then you will know someone else has been there. So that's why it's broadcast. Even if you want, it's the individual who has to go to the location where the signal has been set, rather than having a propagation of the signal itself. But still, it's a broadcasting. And then the conspecific avoidance is you retreat after encountering. because chasing the others, yeah, it can happen, but it's not very convenient. You can have this fight for which everybody is going to be a loser because you can be crippled. So all of that is what you have to call it. It's a send-mediated interaction. So you interact with another individual, not necessarily by finding and being at the same location at the same time, but just finding the scent, so the mark that someone else has left in the past.
This is the pheromone, no? For the ant?
For the ants, it's exactly the same. So for the ants, it's a pheromone trail that they follow. But the pheromone is an attracting signal, typically, unless it's an alarm pheromone. This is you retreat, so it's slightly different. But
so, but is there incentive for the animal to go to the place where there is no scent now?
So when there is no scent, they certainly go because they don't find.
Is there a long-range interaction? That's what I'm asking.
Yeah, I mean there is a long-range interaction because in the moment that you deposit a scent, then suddenly you can be far away from that location and someone comes in. So it's a delayed long-range interaction.
You deposit a scent, you go far away,
Yeah.
and the scent is evaporated.
No.
Do you have an incentive that you know that the scent is evaporated? It is
Oh, I see.
directed to come here. Is it this kind of interaction?
Well, I mean, okay, so at the model, the level of the model we have analyzed, we don't deal with that because that means that you have a map in your head where are the locations. So then you're talking to higher organisms, which in principle that's the case. So you will see that all of this it could be done by a very stupid, let me call it stupid animal in the sense only you have to know is that you react once you find the scent, and that's why somehow you have not so many parameters because you can actually deal with just that. So in fact, just because you mentioned that, so this sand-mediated interaction, there's another name in biology that's been used since the 60s, which is called stig-merging interaction. This is an indirect interaction through the modification of the environment. So this kind of interaction was coined in the 60s by biologists. So it's actually Pierre-Paul Grasset. He was referring to actually eusocial insects, in particular termites. If you think about how is it possible that the termites can construct this nest, which is 100 times, 1,000 times bigger than themselves. Is there a central controller that decides what to do? No, there is none. So what happened is that just the interaction between them, what happened is that they choose some material, in chewing some material, they release some substance. So another termite comes, notice that substance, and so that termite decides also to do it. So there is a feedback that mechanism, and then eventually you have a tower that grows here, and then eventually there is a big one, which just happens to be the one out of which the whole architecture comes. So this happens because you have modification of what the environment is, and you respond to what you find at that location. So that's the same form of stig-merging interaction. So in fact, we wrote a paper. I'm not going to go too much into the details, but there are certain mechanisms that you have to look for to say that it's a stig-merging interaction, and we managed to actually find them in this territoriality model that I'm going to discuss more about it. But it's okay. So you can ask me more about this. So let me go to the model, and when you have a spatial-temporal process, you first have to decide you want continuous space or discrete space. So we decided for discrete lattice. There is some convenience. I'm not going to tell you why. But so you have a lattice. Animals move on a lattice. And wherever they go, so they are random walkers, so they forget where they came from. So the position in 2D, where they go, is 1/4 in each direction at the next time step. So this is when they don't encounter anybody else. At the same time, they are the so-called markers. Now, it's called hinterland to distinguish from the one they call borderland markers. There are some species where they mark only the borders. Foxes, they mark everywhere they go. And so these are called hinterland markers. And so for you live wherever you go and mark. Now, so that mark is only alive or active, and this is an important parameter of the model, you'll see, for a time t. AS stands for active scent, okay? So an active scent time.
This is a random term or
No, it's deterministic. Yeah, I mean, you can put it as like a distribution, not much is changing, but okay, so. They retreat upon encountering foreign. So whenever they go into a lattice site where there is a foreign scent active, so which has been deposited within the last TAS time steps, then you retreat. Now, the probability of retreat, I mean, you can change it. Of course, we have to find ways to change it. If you think about it, just think about it in 1D. This is just so. When you go to the location where there is a lattice site, the probability of retreat is 1, always. So it's presence absence, in other words. I make it very simple. up to the active send time TAS. After that, you can go left or right, or well, in this case, it's one left or right, irrespective. So that's simple. Now, of course, you can modify this. Often animals, they probably, you can imagine you have a probability that goes down. So they recognize actually how old the scent is. So the older, rather than be presence absence, you have a slight modification of that. But so things change in the output of the model if you do that.
So the scent remains there for 1 unit of time.
Well, it's not 1 unit of time. This is it's a continuous time. Okay, this is a continuous time. If you can, or a set number of, if it's discrete time, a set number of steps. Yeah. So now this one is in words. If I give you a snapshot, it's much easier to understand.
Amount of scent release is same for molecules.
Sorry?
Amount of scent
Yes.
release is same.
Same. So that's right. Presence absence. Okay. Now we didn't know what else to call them. So without big fantasy, territorial random walkers. So that's just to connect to the title, okay? So, so that back in 2011. So I'll give you a snapshot so to see and understand the interaction. So that's your lattice. You have 2 animals here only. So remember you have a big lattice. So this is one animal. This is the other animal. So the closed circle. So this, let's imagine it's discrete time now. At the next time step, you can go anywhere in these 4 locations. Equally likely. So it's a random walk. Now it just happens that this red animal, within a certain, within a TAS time steps in the past, he has been here, 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 here. Here we don't say when it has been, but it's still active there. Now, and what about this one? Now at the next time step, this you can see the interaction. He has stepped upon a location where there is a foreign set, which is a red circle, open red circle. So the next time step, he has to retreat. Now you can play around, how do you make the retreat? Do I go back exactly where I came from and so on? So these are little details. So I will not change what I'm going to tell you in terms of results. But so in this specific context, he retreats to wherever there is no red circles. Okay? So, or you can just, if you came from here, you just make it back. So that's, so as you can see, it's very simple, this model. But the richness of what comes out, and these are this typical collective movement model, you have very simple local interaction rules, spatially and in time, and suddenly you have long-range structures, patterns which have much larger scale than the one of your, dealing with in terms of the interaction. No?
So you know whether there is scent at a location or not only after you reach it.
Correct. So that's why it's a very stupid animal. You just stumble upon without, as he was asking, does he know exactly? No. You can actually be very silly. No, okay, that's what I'm saying. So the simplest way, you just retreat where you came from. So now this is, you can actually say that you put up your head and look around, okay? So, but these are very minor modifications. So fundamentally, you have an exclusion process that all that matters. So I'm saying that you can try to play around those, and we did, and not much has changed. So, okay, so in other words, in trying to present these slides, to tell you there is a delayed exclusion process, which is built in, because that's what they do, at the level of individual, but it's actually at the level of the territory as well, no? Because this is, now as you can see, aside from the boundary layer, if you want, the territory exclude one another. So is that what is creating also this echo? Okay. So now I'm going to show you that given this very simple model, I want to tell you about the dynamics of these territories. So I'm going to show you some movies so you get a sense. So I haven't yet told you what is the definition of a territory. Now I'm going to be able to tell you what the definition is given that model. So the territory is a set, for each individual, is a set of spatial locations where we have been in the past TES time steps. So this is the active scent for that moment in time. So if you want, so wherever the animal is within the time t at the moment you say where is my territory, and then t minus TAS time steps. So that's your territory.
So Luca, it seems that the battery probably
Oh.
unless, or you have some coins or something, because there's some feedback coming.
No, I have no. I have a keys here.
So maybe
Should I
remove
put?
the key, because like any metal thing will. Oh, because of the AC. Okay. So let me just switch on. Because continuously there's some.
Oh, okay. So, so I give you a snapshot. So some initial condition. Each color is a different scent, and each non-white color, so non-white color is an active scent. I'm not putting the information when was it deposited at that moment in time. And so I'm going to show you a movie of this at every TAS time steps, because if you go every little time steps, I mean, you have to wait forever, no? So I just, you know, sample it.
There are still 2 workers or many workers?
No, it's many workers.
Many workers.
Yeah.
Different set. Each color is a different kind.
Correct. Each color is a different animal. It's a different scent of the animal. So
and the range of the scent is the same for all.
the range of this, what do you mean the range of the scent?
I mean the time they will take to vanish.
Yeah. So the TS is a deterministic, as I said. So it's, you know, so the stochasticity comes about because of movement. So you don't really need a different T for each one.
But the movie depends on the initial condition. It's
No.
not like
Depends. Yeah. Of course, you know, you have to run.
the initial conditions which is completely trapped, which is in a what you call recursive cycle. Like
Yeah.
Just for example, the one animal is trapped in the scent of the other one.
Yeah, but
You
that.
just can go on it.
No. If it can happen that, and you will see there is an initial condition I put on purpose, or you see, and
So
one.
only the whole result will depend on this is the initial condition dependent result.
Yeah. But I want to give you a sense of what is happening depending on the value of the active scent type.
Okay.
So you have a fast dynamic and a slow dynamic. So now look at the movie. So just pick a color and just follow it if it starts. So that's a fast territory case. Yeah. And so the movement, so whenever you see, you can have white spaces inside one territory because it means just in that location nobody has been in the last TAS time steps, no? But you can see that's what I call a fast territory movement because you pick a territory, it goes anywhere, I mean, in your window if you want, no? So
one animal with each set.
Different color means different animals.
But number of animals of this.
It's just one. So I don't have a family unit, it's just one, yes.
I think the battery.
That's why he's doing that.
Yeah, probably.
But I mean, I actually have, I mean, I talk very loudly. Do we need that? No? Okay, let's see. Okay, so this is a fast territory. Now, now I'm going to show you the case of a slow territory, and on purpose, so you ask me, I just put on purpose initial condition. You see, one is localized, and you will see there is no way it's going to be trapped there because these are random walkers. They tend to exclude one another, and so eventually that will grow. So. So this is a slow territory dynamic. So the TAS, you know, it's twice as large. So there is an exponential dependence on that value. You see that it's growing. Now this is a more probably biologically relevant situation because each neighbor is going to have 6 individuals around it. So there is a tessellation on the ground to that. So this is more. And so what you have breathing territories because everybody trying to gain access to the neighbor, but only when the neighbor is not there for a sufficiently long time. So because you study. So in other words, for that to move, it means that somehow you don't see it in the movie because it's sampled at the KS, but something has become white, and you have been, as an animal, you've been there, you've deposited them, and so it's quite a complicated process for that territory to move. But so this is, so just to tell you that the importance of TAS makes the dynamics very fast, very slow. Okay. This was just twice as long, and then the sampling is here. So it's big difference.
So can one think of it like some spin dynamics? So there is a spin which is up for some time.
Yeah, so there are many spins though. Yes, if you want, you can think about Q-pods, no?
Q-pods.
Yeah, so you can think about it in that sense.
So what will can one think what if
No, please, you should ask, so that I'm sure that help everybody to understand that.
no, if there are two
want to tell you is about the, I mentioned that there is a definition of the territory. I gave the definition of the territory. Now, let me just say what a home range is. Yeah, tell me. Oh, no? Sir? Yeah, now it's working. So, well, okay, so as I said, I've defined for you the territory, what is a home range. And so this is important for me to tell you, although it's just one slide, and I told you that I'm not going to discuss much about when and where to measure these territories in which you actually measure home range. In the sense that it's very difficult to measure scent. So what you actually end up measuring is where the animal has been. So this is a time-integrated position. So I constructed this probability of occupation integrated over time. And so what you have, you pick one of those movies that I showed you, probably it's, in between the first and the second in terms of time scales. And you see there is an initial condition here. And then you run the simulation. And then you record where this animal has been. And then what you get a structure which has what is called the home range. Or sometimes animals utilization distribution. Each one will be segregate in a different region of space, obviously, but look at the heterogeneity of what comes up. Now, if I really have to show you the 3D version of this, so this goes, out of the out of the room, because it just happens for that observation, this remain trapped to some extent compared to, and then this happens when you have, 3 which are much bigger around it. It comes about because of randomness of the movement. That's all. But if I wait, a large number of time steps again, all of this, and I start re-measuring again, all of this will move, okay? So everything is always in flux to some extent. No? But, so this is the sort of data, well, nobody has such resolved data, really, even with GPS, but this is the sort of data that, you have to analyze indirectly if you want to say, my model is, is working or not, no? So if you really, but, okay, so this is what the home range. So I just want to make you aware of that. I mean, we're not going to discuss much about it. So, oh, the contour line. So this is the actual value. I mean, this is the actual value. So this is the frequency of occupation of an individual of that scent. So the specific individual, that's. So it's a probability of occupation integrated over time. So that's so. If you you start here. There is no scent around, and I just wait, and then I forgot how many time steps I did, but. So all I want to tell you is that, remember that there is no resources the animal consuming. So the message here is that the heterogeneity is endogenous generated. So it's all dynamic disorder. There is no quench disorder in this model. So this is the amazing aspect of it. So.
But in the actual data, there is also population. It's not only scents. Like two different set of foxes, they can have, the population could be different. So it can not be.
What do you mean? You have two different kind of foxes, two different species you're telling?
No, like the Bristol fox probably on the same. So there can be two different social groups, but the number of people, the number of.
Oh, the family unit.
Family.
No, yeah. So, but you will see that actually the red fox, they're actually single unit. Only when, no, the point is that only when, it just happens that, in fact, all this investigation started because I was talking to this colleague of mine in biology, and he was telling about foxes and so on, and then I learned a lot about these foxes. So they only are not a single unit family when they are just looking for the mate in that period of time. But all the rest of the year, they don't. So they're really individual, okay? So then it does fit perfectly. And you'll see it also fit for the fact that we have no resources because in the city, these are scavengers. So they have 120 times more than what they need. So it doesn't matter to put the resources, okay? So, but that. So when I'll tell you when I come back. By the way, I don't know when I started. Shami, can you tell me when?
Half an hour, more than half an hour.
Okay. So let me go to the specific of the model. So what are the parameters? Since I told you sufficient is simple enough. Okay, so this is an important parameter. So the time beyond which sent has been deposited vanishes, if you think, or becomes uninformative. So TAS, active send time. Now, then you have a lattice, you have random walkers. So we are talking about continuous time, so you have a jump rate to move, in one of those 4 potential positions. And you have, of course, the last parameter is the density, which you can, we'll see it's convenient to talk in terms of the inverse, but so D is a dimension. So in principle, this model could be in any dimension, could be done. No? So think about D equal 2 for the case that I'm going to tell you about. And so this, you really have, once you define the interaction, you really have just 3 parameters. And now F can just be rescaled, so at the end of the day, you just have 2 parameters, which is active send time and the density. That's all you have. So what is the key parameter? Okay, I have 2 parameters, but actually, in investigating the model, it turns out that there is one parameter that encompasses nearly all of the dynamics, which becomes important, which is spatial competition. So you have to think about the ratio of the following spatial quantity. You have the space occupied by an individual in the absence of others. So this is a random walker. And so within a certain time, we'll try to, explore the entire space available. So then if there is nobody around, there will be a certain amount of space. And what becomes important in that active send time? But this is where you create your own territory. So that in principle is a unit of your territory if there is nobody else around, of course.
No, what is the space occupied in the absence of others?
Yeah, so because you're trying to look at the interaction, so therefore you make a ratio between what the individual would tend to occupy versus the actual available space. So in fact, therefore that's why I'm saying in the absence of others, and then the ratio is to what's the other length scale? It's the average space available when there is the population of inverse population density.
The mean free path or something.
That, the mean free path, if you want, it's related to the top when there is nobody others, yeah. So, yeah.
And this average is over average space, so this is over all the species.
This is the top one. The top one has to do with nobody else, so it's an ensemble average if you want. So because there is nobody around. The other one is the inverse of the population density. That's all. That's the average. So in that sense, although you have seen territories can be at different moments in time like this, but there is an average size available. So now, how do you actually compute that Z? Because you want to, So and the top one you can think about. I can just think about the average number of distinct sites visited in n jumps. Now, since you're talking about continuous time, FTAS. But if we were just running in discrete time, you just number of steps. Huh? So now, what is that quantity? Well, that quantity, so this is the problem. Sometimes I have this slide here. Oh, no, it comes out. So in D equal 2, that's your average as a function of n has a very specific dependence, which is nearly linear. Now, these are, for those that know, this is some log dependence. So we did our simulation, and it turns out that you have a coefficient that will depend on the lattice you choose, if it's a rectangular lattice or if it's a triangular lattice, that changes. But the dependence is n to the 0.1. So these are your the exact result of simulation, and then the approximation, this one is much better than the Montreal one for a longer range. So we picked up that one. So in other words, you can represent that Sn, which is the numerator of that Z, as some constant to the power 0.91. So n is the number of steps. And therefore, your Z is nothing else than the ratio of your Sn divided by, n, it's fixed by the TAS. Huh? So there is a, remember, it's like if I write TAS to the 0.91, divided by the inverse of population density. So now, remember, I was telling you about I have two parameters which are important, the active send time and the density. But actually, what I'm telling you is that, no, there is one parameter that essentially defines the entire dynamics of the system, or the regime of dynamics that you will see as you go on. So now, you have different regimes of interaction. I'm not telling you about all of them, but because you can imagine there is a regime which is, everything is jam, so you have a super high density, so it's a very different regime, or you have a very, very low density, so it's also very different.
So n number of steps, that can be large for large number of steps or exactly
No, that's for n essentially, if you think about discrete TAS, think about n is equal to TAS. So how much do I occupy within that active send time? I just make the specification because since I've run it in continuous time, then I have to do FTAS. So the number of jumps within that, that could be, that n can change because it's random, no?
In the time scale, what the same states?
But if you think just to intuitively, it's equal to TAS time step in a discrete setting. So now, so is it really only depending on that? Not quite, because there are different regimes of interaction. So actually, there is dependence on nu and TAS separately. Although, so remember, so nu as you make nu larger, so nu is lower than 30%, so it goes lower density. So what you can see is that there is. So what I'm plotting here is the ratio between the average territory size divided by the standard deviation. So, and as a function of z, so there is some behavior which is very common to all of different values of nu and TAS, but actually you don't capture everything. Although what I'm going to tell you is that I'm going to talk to you about specifically what you see now about density, which is the inverse, which is 48. Remember, this is dimensionless quantity. Yeah? So because again, you have those regimes where you have everything is jammed. It's a very different kind of statistics, and everything is so few interaction you have, and you have to wait for so long and so on. So that's okay. Just specific about this. Anyway, so let me just tell you. So I think you got an idea of the model. So you have a territory at a certain, let's say, mesoscale, but then you have the animal at the microscale, and then if you want the patterns at the macro scale is the one that we observe. So what happens if I look at the dynamics of the animal? So if I look at the dynamics of the animals, for different value of z now, so remember, we are going to tell you everything in terms of different value of z. I look at the mean square displacement, so that's a variance of your occupation probability. So I do an ensemble average of that for the same initial condition. That's just to tell you that in this case, I keep nu fixed, as I told you before, and then all I'm changing is TAS. So the z value that I'm looking at for a fixed nu, and I'm changing TAS. So I'm changing the little n in Sn. And then what you can see is I plot with the normalized time, and this is also a normalized. Remember, I have a window of observation because I have periodic boundary condition. It's a triangle, but all that matters is that the dynamics, it saturates because you have a window of observation, but this is fictitious, just because I have a window of observation. So this will keep growing forever. Huh? But notice the difference as the dependence of this mean square displacement, so which means how much you occupy in space, the area you occupy in space on average, as a function of time, depending on the value of z. So depending on the spatial competition. So if z is very large, so 15, so essentially you see that there is linear dependence. You encounter nobody within that time scale, but then you actually encounter others because they're confining you there. So you remember, if you have a box and you look at the mean square displacement in a box, then your mean square displacement goes there and it becomes flat forever. So this one is not really flat because eventually it grows, but such a low time scale. Look at this. Is talking about the logarithmic scale, okay? So everything gets slowed down. So you have a sort of a caging effect. The larger z, the longer this caging occurs. And if you think about a value z which is around this range, then you see, as you can see here, there is you encounter the boundary is the presence of the neighbors, but then eventually you escape them pretty quickly. So, okay, so that's good. So this is it's sort of a clear understanding of what's going on. Now, the question is, do we really understand? Can we really say what are the regimes by looking at them mean square displacement? No, because it's continuous. Do we really have different regimes? And so in order to look at that, to answer the questions, what you actually have to do is to look at the mesoscale, at the territory. So that will give you an answer. We'll see that we'll have different regimes. And to do that, you have to sort of coarse grain, temporal and spatial coarse grain the dynamics. And so I'm going to show you a movie that this gives you an idea of what we did. So you zoom out, you look from far away, so you're zooming out, so you're coarse graining spatially. And then you will see that after I've done that, so I'm looking from a distance, then I actually coarse grain in time. So I integrate over time. I look at the dynamics every TAS time steps. So it's coarse graining in space and time. And so the video here should actually.
See the previous slide.
Yeah.
One question
Yeah, so this, the difference is this coefficient C. So then the value of Z will change. So we are going to see for different Z, different regimes. And then you can say if I have not the triangular lattice, the other lattice, you know, the value of Z, where that happens, that changes is just slightly different, but this is very minor. So the coefficient is 0.67 versus 0.72. So it's just, it's very, very minor.
So the slope of all these are almost the same?
The slopes, I mean, well, here they are clearly the same. Here they're not, because, you know, it depends on the slide, I mean, but
they eventually tend to something.
no, they keep going, you know, this, they go to infinity, because eventually, although it's very rare that even at high density, you have to wait a long time, but they eventually will move all over. Is that what you're asking?
So, yeah, so in a sense, so the slope of this is the power law that relates the mean square displacement with the.
Yeah, so you can actually, yeah, correct. So you can actually try to fit, I mean, you can actually have a bigger system so that you can fit properly some exponent and, oh, thank you. So you can fit properly some exponent, but the question is that even if I would have done that, then I just tell you the same as I'm telling you, I'm just characterizing. I'm not telling anything about what regime is that. Well, I have a different exponent. Have I gained something? Not really. So that's why you have to go to a different approach, which is looking at the mesoscale. Huh? So if I actually, sorry, now I have this one that should work. Yeah, fantastic. Thanks, Shamik. So, but probably I have to point to it. Yeah. Now, so as I said, this is a special coarse graining, spatio-temporal coarse graining, I tell you. So I'll show you. So.
No, I think the question is that n. So you have plotted up to some n. So
Okay. So now I'm spatially coarse graining. So I'm zooming out. Now the frame is 1 step, but now as I'm, you know, as a system, as I wait a little bit longer, now I'm looking at frame over many steps up until TAS time steps. And then when you go at the active SEM time TAA, all that matters is the dynamics of the boundaries. Not much is happening there. And then so then you can think about, but then essentially I have, you know, particles with variable size that interact one another, if you want to approximate. So talking about, you know, the surface, what happens to the dynamics of the surface. So at the end of the day, you can just think about that system at the mesoscale, so the level of territory, as particles which have a size and an interaction potential which is soft enough so that you can actually change. So if you can think about that. So this is, so that's what allowed us to actually see and answer all these sort of questions. What is the regime of interaction? Because that's what good enough. So we actually essentially did a coarse grain in space and time. In fact, if you do that, all that matters turns out to be the centroid is good enough to actually understand a lot of things. So in fact, so this is, remember, this is what you might think, oh, yes, I have a quantitative handle of it, but you have really an understanding? Not really, because if I now show you the centroid, for the different value of Z, then you start having an understanding of it. So these are just the centroid after, I mean, the system has run for a long time. And then what you can see is that depending on the value of Z, the larger Z, the more order there is, as you can see. So this is very low Z, there's no order. This, you start seeing some order. That, certainly you won't say it's a solid, but there is some sort of a solid there. And then this piece looks like really a solid. Huh?
So there is a keyword for, so there's a keyword for this kind of structures called hyperuniformity. There's a new stuff.
Okay, so you can tell me that. I don't know about it, but you know. So, but yes, sorry.
What happens if you're coarse graining and then you scale the things also?
What do you mean scale?
You are coarse graining. So what is the, since you were saying about the spin model, something like
Yeah.
the spins.
Mm-hmm.
So if you coarse grain, the average of the spins, and then scale the spins also.
You renormalize.
You know,
Yeah, I don't know.
So I'm just asking whether this is
These are all different.
discrete renormalization group type of thing.
Okay, so that, okay, I'll be happy to discuss more. I don't know. Yeah, so I haven't even thought about it. Yeah, serious.
And this FT is you have plotted up to 10 to the power 5 or something.
Sorry?
You have plotted this FT.
Yes.
X-axis here is 10 to the power 5 or 4 whatever.
Yeah, yeah.
But then, you know, if you take very large, then eventually all of them at some point above some n star, which is a function of Z, it will be probably the same slope. It looks like that's what is.
Yeah, so I mean, eventually everybody will come out. So this caging is only is only temporal.
Yeah.
So it is a transient caging. So, but again,
So
imagine.
when they come out
Yeah.
of this casing, they will always hold the same slope.
yeah, so eventually then they will, no, they're not going to get slow. They're going to be changing, as I said, to the previous capture. They're going to different exponent as they go. So you can see here, they're not necessarily the same. No? So that is another way of characterizing this. But again, I thought that this would not have helped me. And besides being extremely complicated, here you're talking about a month or two simulation to get this data. Okay, so that's. So in other words, once you get this kind of structure, then it's very easy to ask the question, well, I mean, what kind of order do I have it in? So in other words, what kind of phase I'm in? And in fact, you can talk about, is it a gas, is it a liquid, is it a solid? I mean, obviously, no? So how do you measure those? Well, you just compute pair correlation on the actual data. So what is a pair correlation? So it's a sort of probability of finding, it's not actually a probability because it's normalized to the case of the ideal gases, you will see when I plot it, but it's telling you what's the chance of finding, given one particle, what's the chance of finding, as a function of my distance from here, from my center, the next particle. No? And so if you actually plot for the different value of the different z cases, then you see you have a different qualitative features that comes out. So this is a classical situation where you have a gas. So remember, all these curves are the pair correlation function as a function of the radius, but they've all been, so they all start at 0, so they've all been misplaced just for you to see it. But you see, when you have this sort of different peaks, these are the waves of neighbors, So if you think about this. So you just put yourself in one location, and then you have a range of 6 neighbors, more or less. That's where you have your first peak, that comes up here, no? So there is nobody just next to me, and then if you have a solid, clearly there are specific distance where you can see, and so these peaks become sharper and sharper, as you can see here. No? Now, since this is plotted as a function of the radius, now it's a normalized radius, but notice that when you are in this regime, which is probably look like a solid, then the peaks breaks. Why? Because I'm plotting as a radius. In a solid, I mean, the symmetry is not radial, it's hexagons, okay? So it's different. That's what you will see. No? So in fact, in the colloidal literature, as soon as you plot the correlation function of real data, as soon as you see the breaking of the peaks, then you already say, oh, that's a solid. I mean, you might have to use different techniques to find the transition point, but that's what it is. So this one and this one, if you look at these two, actually, then you look, they are qualitatively the same. Although when you look at those, they're very different. So therefore, the pair correlation function doesn't help you to distinguish them. So we'll have to do something else to see. But this clearly is, probably you can say it's a gas now. And then once you plot this, the question is that if I want to know what's my regime of interaction, then you just have to identify the transition points. Huh? So then the different phases comes up. So now, just to see that how you can distinguish these two, if I go in the 2D pair correlation function, now I don't integrate over the angles. So for those cases, well, it's probably different value of z, but then you see there is radial symmetry here and here, and you start losing the radial symmetry in the third regime, which looks like a solid but not a solid. And then you've completely lost it, and that's the breaking of the peaks in the radial version of it, which is here. Then you really have hexagons, and that's the geometry of a real lattice. So now, for those that know, I think it was 2 years ago, there was a Nobel Prize on topological phase transition, so this has to do with, Costa and Thales, they got a Nobel Prize, but so other people work on it, and so this is the theory of phase transition for 2D lattice. It becomes important that the topological defects, and what you have is that if you have a 3D object, you increase the temperature, you melt it from let's say from solid to liquid. No? But in 2D, in some cases, you have an intermediate phase, which is called the exotic phase. And so this has to do with this topological defects, as a way. I'm not going to tell you much about it. But so now, do you remember that we had two phases that have the same pair correlation function, the radial pair correlation function, but they were actually looking very different. And so then the question we asked is this really an exotic phase, the one intermediate between the liquid and the solid? No?
Since you raised this, so what is at the level of the animals, what is the meaning of a vortex solution?
Of a vortex solution?
Because that is the
okay, so let's say like this. Yeah, I don't know, but all of this become important when you look at data. Because if I try to answer a question by this general theory where you need this massive amount of data to actually answer this question, it's going to happen. But if I really go in and try to identify these defects precisely, so what is a defect, in the terms? Is that simply, one having 5 neighbors rather than 6 or 7 neighbors and so on? So that's what may help us, going after data and saying which regime you are. Rather than, having that kind of data that you need to answer in this way is not going to ever work. So to some extent, those questions comes about, as you do that.
Yeah, probably there is no obvious vortex, anti-vortex pairs that forms here, no?
Yeah, I mean, again, I haven't answered because I don't know, but I know that once you actually clearly find the ways to measure in terms of these territories, what these, defects are.
There must be some analog, because since you're using this cocktail service analog, so there has to be some physical analog for the vortex solution.
Yeah, yeah. But what I'm saying is that I think, again, I don't know for sure, but I think that the defects here, when you have, binding and binding of so when you have 6 neighbors, that's perfect. But when you have 5 or 7 neighbors, that's when you have, so then when you have dislocation and disclination and so on and so forth. And we sort of see that there are this pair of disclination, dislocation, and binding and so on. We haven't studied yet the full details, but this is, that's where we're interested in. So just for you to know is that, again, as I was saying, so if you have a crystal and you increase the temperature in 3D, you just have, you have a first order transition, you get a liquid. But in some cases in 2D, so you get this dislocation and disclination defects that appear, so they appear in pairs, and then they become free, and then you get a liquid. And so notice that, I just want to notice that what happens this dislocation is that you take the set which were next to here, and then you displace it a bit. Now notice what happens is that if you look at this guy here, the number of neighbors is the same. The position in terms of at 60 degrees is the same, the neighbors, the first neighbor. But the distance now is not the same. Notice the distance here is different, no? So compared to the actual perfect, hexagonal lattice. So this is what distinguishes an exotic phase from a solid phase. So the distribution of distances is not the one with the perfect one of the lattice. Is different. On the other hand, the position in terms of the angles where you are in, it's the same. So, and this is precisely the exotic phase. So what you have to do is that, so we believe that what was the case, and so we looked after. So is it really an exotic phase? So what you measure is actually this bond orientation order. So when you look at this phase transition, then there are this, or the parameter that you look at, this has been studied in solid state physics, so we just had to borrow this. And in fact, if you put pi over 3, which is 60 degree, so this gives you 1, so it's a perfect order system. And if it's not, then you probably have a liquid and so on. So, and if you actually plot for the different phases again that I showed you, for the different z, so this is the exotic, this is a solid, and they're essentially the same, because you're looking at the bond orientation order. So what's the position of my neighbors? And they are perfectly at 60 degrees, more or less. And if you go to a liquid or a gas, it's not the case. So that's why you can see that's an exotic phase. Now, and to see that it's precisely an exotic phase, now if you look at the radial distance, so the bond, so the translation or the parameter, as you do the same, now you're going to see differences. So this is, I forgot with that value I've used here, but then you can see there is a difference because now suddenly the distance is not the actual, the one for the lattice. So in other words, we were able to identify different regimes. Once again, I remind you that looking at the animals was not sufficient. I mean, yeah, you can have a handle of what's going on, but are you actually able to answer what regimes you are? Not only if you go to this mesoscale. So to some extent, generally people say, oh, I have a model, okay, let me make it more complicated and let me go to the microscale. No, what I'm saying is that no, you should actually coarse grain. If you coarse grain, you get a better understanding. Well, okay, you can say it's specific to the model, but I think it's, in ecology, there are many examples that it's actually better to do that. So once again, so these are the phases of the territorial centroids that, so this is, again, this is the last.
XY transitions, costly Thouless transition, that also justifies this varying power laws, right?
No, okay, the power, okay, so, okay, we had a difficulty, let me tell you. We had a difficulty, so, of identifying the power law, and we went through this, just a bond orientation parameter in that, because, yes, there should be power law, but we have an underlying lattice. So that underlying lattice, whenever we were looking at this power law, we didn't allow us to see. That's right, but you're right, absolutely right. But this is, yeah, so you can probably relate this power law that you can find here to the power law that come up when as the pair correlation function decays. Yeah, but we couldn't. Yeah, but we could not because we had this underlying lattice which was imposing some sort of order that was just fictitious because it was the underlying lattice, so we could not. Yeah, it's a good question. So now, so as I said, we had the tools to say when you have these different phases, but then when you find, how do you find these transition points? I have no idea when I have to. Okay, 10 minutes. 10 minutes, okay. So, and how do you identify this transition point? Well, now you look at some global order parameter. So you look at all of them because these are, the one I was plotting so far were always related to the individual particle looking, So you take this global order parameter and you look at the susceptibility. And so this is the global order parameter, so it's a modulus if you want. And this is for the translational, so this is for the translational order, this is sort of psi 6, which is the bond orientation order. And then, okay, we are trying to see if there is some sharp transition happening there. But what becomes more useful to determine the position is the susceptibility, which is nothing else that you take this global order parameter and then you take the system size, and you just reduce and reduce and reduce. So to some extent, this allows you to do a scaling analysis. We didn't have enough data to do properly the scaling analysis, but you can see, you can identify the phase transition to some extent kind of precisely within the resolution of our Z, which was 0.25. And then you can see that, so the exotic, which is a psi 6 value, we could identify 9.75, and then the solid is, just like, so generally the exotic regime is very narrow and so on. So, okay, so this is to identify the point. So, in other words, you're able to say what are your regimes. And now the question is that, was it the first order, second order? So that comes about, so evidence for us was, remember the KTHNR talks about exotic liquid, and exotic solid, which are both continuous. So you have your second order or continuous phase transition. Now, that, for our case, what we were thinking also, but there is also more recent evidence that you can have a first order, so the first exotic liquid, so the exotic liquid can be a first order rather than a second order. You still have a second order for the exotic solid. So, and that has to do with the potential of interaction of the particles. So it's a very hard disk, so interaction is very stiff, sharp, so then you tend to have, first order. On the other hand, as you get to, a potential, so this is a really, I think it was Werner Kraut that studied it. So if you have actually potential which is softer and softer, eventually you get a second order. So in our case, we don't really have hard disk. As you can see, this, this particle, they breathe and so on. And if you think about in the way we approximated that, they overlap. So there is a soft potential there. We didn't know exactly how to quantify, but, and so that, therefore for us, it was, more, the actual KTH and white theory that, so that's probably what, it's really happening. So just want to tell you that what, at the moment we are analyzing, besides the defect aspect, trying to get at, so the question is that, well, but animals do feed, no? So why we cannot really neglect it? And so now, so we just started, but what I'm interested in showing you some videos where we're just looking at, suppose that the animal has some memory, now speaking about higher intelligence, okay, so have some memory where the food resources are, where they've been successful. And so we're trying to put in, some more ecology. Now, the unfortunate aspect when you do these kind of things, then you completely lose ability to do some approximation and so on, because, then becomes a very, even more complicated simulation. But, okay, let me not spend too much time on this, but just to tell you that now the size, so I'm showing you the, here I'm showing you the size of these balls is in that moment in time the size of the territories, in approximate fashion. And this one is where the resources are. So this animal never die, but they try to actually go and stay around the resources. And what you can see is that the size around where the resources are, the size is smaller. So somehow, because they tend to return there. And so, I mean, in ecology, it's natural that those that are in a region where there is lots of resources, they don't want to necessarily expand. I mean, why would they expand? They just have to defend their own area. So this is just a sort of test to see that that's happening. Okay, so just to tell you that you can build and make this model more complicated and so on. Now, in the last probably 5 minutes, I'm going to tell you about the analysis of the data and so on. Now, when you have this complicated, or at least time-consuming simulation to do, and to look at data, if you want to use the simulation to actually look at the data, it's kind of a nightmare. So one of the things we were thinking about, okay, so let's find an approximate model so that we can actually apply to data. So the way you go about thinking in that is that you focus on an individual, and it's not going to be valid for any regimes, especially not going to be valid for the gas regimes. But in the case where you have high density, enough high density, or TAS is sufficiently large, that's what turns out to be the working case. So, and you start again, although we go in 2D, but you start again in 1D. So what becomes important if you think about an individual, and when you do this kind of mean field approximation, is that you have one individual in interaction with the field of all the others. So that's a classical mean field. So you focus on individual, and what becomes important is that just think about 2, and then we'll think about 1. But so in a 1D case, you have the individual that diffuses, and then all that matters is when it encounters this red scent, which is the extreme value of the excursion of this guy. All that matters is that. So in other words, you have one individual and 2 barriers. So it's a 3-body problem. So if you make this in periodic boundary, that becomes really a 3-body problem. So what we did is that we look at the simulation of this simplified version. So you have a ring, you have 2 animals, and then you look at what happens to the mean square displacement, because simply we have it from the data and so on.
The space is infinity?
No, just it's periodic. We just made it periodic. So again, once you have a periodic, so you make it finite, there is some value for eventually you can talk about. It's fictitious, but again, there is an exclusion process, and then in 1D, the mean square displacement grows as square root of time. So we just wanted to make sure that this is, although the exclusion is not between the individual, it's between the boundaries and the individual. But of course, you have to get that exclusion. And in fact, if you do the simulation of that system, well, trust me, this is square root of time. Just trust me. But, So it's linear here, and then it's so this is the statistics of the position of the boundary that actually it's Gaussian. But that's what you expect. Now, if you look at the distribution at the specific moment in time of your probability of occupation, then obviously what you can see is it's a sort of flat top, and then at the boundaries, it becomes shallower and so on. But remember that this, once again, if you wait long enough, I mean, this will occupy the entire space, because again, you have this finite size.
Is it a 3-body problem? What's the potential?
No, they just this is an exclusion as you encounter. It's like a box, but the box has a varying width. Because it depends.
Hardcore.
Yeah, it's a hard. Yeah, it's a hardcore. Yes, so it's an exclusion.
Yes, I just had some information, right? The 3-body problem with the delta function potential, it's exactly solved.
Well, yes, yeah, okay, yeah. So yeah. So you will see. So what's the analytic model? So that so again, this is a 3-body problem. So we are interested in finding the position of this individual walker, which is at some x. Then you have a position of the left boundary L1, and the position of the right boundary L2 as a function of time. That's what you're interested in, So the dynamics of that, if you want. Now, and that you can write in general terms. It's the probability of having a right one as a function of time multiplied by the walker position x given. So that's absolutely general. I have made no approximation yet. Given your L1 and L2. And now you make the approximation, right? So if I think in that terms, then what I say that one, so it's sort of an adiabatic approximation. When you have high density, what you think about, so these are moving very slowly compared to the move of the walker, because you have this active scent time that doesn't make, nothing changes, And so that's, and so what, what you can say, so this is when it works, you can actually phenomenologically represent, there is a size for which this L1 and L2 will tend to, which is the inverse of the population density. And so then you can just think about, you have a spring with some spring constant that makes this of size L, which is the inverse of population density. And then you have a walker inside that moves, and whenever it encounters wherever the position L1 and L2 are at that moment, it gets reflected.
The boundary also moves diffusively, isn't that?
Correct. They move diffusively, but actually, in the 1D, they move, subdifuse the square root of t. Okay, so in 2D, it's time, it's linear in time, but yeah. So, but you're right. So in other words, you put by hand the statistics of the movement because that's otherwise you can't do the approximation. So, and so in other words, if you really want to write the Fokker-Planck for the Qs, is that again this is a moving by hand in terms of the statistics. So you make 1 over square root of t so that the mean square displacement is square root of t if you want. And now the potential is right minus left minus the inverse of the population density. So that's where they tend to. So you have a spring force between the two. And this is your dynamics of the Qs. So, and L1 and L2, they diffuse. And it turns out that, just you can easily see that you can separate and solve this Fokker-Planck even if it's 2D because you just talk about the separation and the centroid and you can actually separate and have 2 equations to solve, and you can solve that one. Now, the Walker dynamics is your standard diffusion, and then you have reflecting boundary at L1 and L2, whatever L1 and L2 might be. So you can actually solve that, and you have the dynamics of WXT, and notice that it depends on lambda and capital L, which is the boundary centroid, and lambda, which is your separation. No? So it's all linked. So now, do you remember that I showed you the simulation for the ring? So then what you are interested in that comparing, for example, the mean square displacement and what you have. So you need the second moment of your x, well, if you want minus the mean, but the mean is 0. But then it's between value L1 and L2, but the value of L1 and L2 can be anything. And so you sort of integrate over all possible value of L2. So it's a triple average that you have to do. But then when you plot it, all that matters, a long times, is precisely this phi of t, which is the statistics that you put by hand if you want. And so,
Shouldn't the L1 always be less than L2?
Sorry?
Shouldn't the L1 be less than L2 or something?
No, because it could be any value, but no. So, yeah. So you can show that. Well, it's inside here that L2 is always so that's why it's. Oh, I see what you mean. Yeah. Or you can actually compute it by a slightly different way, but then yeah. So now and you can see that indeed you get what you were getting in the simulations, and so to some extent this is sufficiently good model. Now that you can test when it works, and then certainly it doesn't work when you're in the gas regime, but in the liquid when the density is high enough, when the exotic and the solid regime, that's actually how it works when you go to 2D. And so this is the general approximation we're going after. So last slide. So to tell you about the fitting of the Fox data. So, as I mentioned before, foxes in Bristol have plenty of food. So it turns out that so in other words, you are not defending for food. So you're just staying there because you want your own area for yourself. So the model worked quite well, and we use the analytic model, and so we actually fitted the data. Now the data fitting, so animals are not really random walkers, so you have to sort of just modify a little bit the model. So we have 5 parameters, and if I just tell you what they are, so it turns out that you have the speed of the other animal. So a random walker has between steps has infinite speed, really, because it jumps. And so then you don't really have that. So you really have a speed. Now you have a sort of boundary diffusion constant. You have a correlation at time. The animal is a correlated random walker, so it tends to move in the same direction for some steps. And so that's what you get out if you look at the data. And then you have this territorial renormalization rate. Do you remember I told you about the spring constant? It's a phenomenological rate that you get out because you just put the model. And then you have the average territory size. Okay, so where it comes out. So when you do, so this is just pictorially. So you have to choose a geometry. So this was 2D Euclidean geometry. We also tried the radial geometry. So not much is changing in terms of the value that we get out. So, but these are the data. We had data of these foxes even have 80 days. No? So you just track an animal, then you find it because it has a tag, that is, and so you find it 80 days later. So then you use that as a data point, as you do the fit. So now, what was interesting about foxes in Bristol is in the 90s there's been an episodic of mange, which is a scabies disease. So the population went from very high within 6 months to very low. So there was a perfect natural experiment for the model. No? So poor foxes, so we had data which were pre-mange and post-mange. And so remember that one of the things that stress you about is that what becomes important here, distinguishes the regime, is the active send time. So now you can indirectly determine this active send time, thinking about how much time it takes for an animal to enter the territory neighbor, because you certainly have to wait an active send time, and then eventually, so as we put in the model, I mean it's a complicated fitting because you go between simulation and the 2D approximation. So we managed to determine that the active send time before the mange episodic was 5 days. So this is a maximum likelihood. That's why you have very little error, and 3.3 days. So to some extent, either you can think about that the chemistry of the send has changed, and so then you can actually answer that way. Or, which is probably more likely, so the animals, after the episodic of mange, these foxes move in the middle of the night. Really, at 2 a.m., if you walk around Bristol and there is no car, you can actually smell the foxes, and you can actually also hear the foxes moving. Yeah? So if you're if you're very careful. So they actually, therefore, when we talk about in the model, they have an active send time, and they wait for that before they actually intrude into the foreign territory. Actually, it's not really true. They actually have other cues they listen to. So if in the after the episodic mange there was they couldn't hear any noise, coming from the neighboring yard, then they knew that the neighbor that they knew who he was not there anymore. And so then, instead of waiting 5 days, they probably tried to wait 3 days. So that's probably what has happened. And then, of course, as you can see, once your size of your territory is twice as big, then you have to, so where is the speed? So you have to run twice as fast to cover it. So that's what how to do it. But OK, so I finish here because probably over time. Thank you very much for your attention.
We are running behind schedule, so let's have only 2 quick and urgent questions. If not, then we go for tea and then we can discuss the quick and urgent questions. Not, so then, so there is not.
If you take the retract probability, retracting with some probability, then by changing the probability, you might have a case transitions, like coexistence of 2 different species versus one species completely irregular species.
OK, so I think what you are referring to is, do I have the figures? Yeah. So, yeah. What you are referring to, so when I was talking about the probability of retreat, so there was tau over TAS, no? So that was 1/2 for the 1D. It would be 1/4 for the other case. But so you're saying that suppose that I actually, when I do something, just to pick something like this, no? Now suddenly the probability of this is not 1. So then, this was actually we studied that model. So if you look at that kind of model, then you have your territory overlap. So in other words, those kind of plot at each moment in time, what you get these things. Okay. So and you do observe this. So that as you change this interaction, which is not purely exclusion, and then you do get these kind of things, and this is the reality is that you will never have this is like having a glass wall, which is not the case. The reality is that they do tend to have some probability, and depending how old the sender is, to actually let me try to go further, even if I've encountered it, because this is sufficiently old, no? So that's what they is. And this is the reality. Now, what kind of phase transition we have? We haven't studied that. So because this analysis of phase transition just came later. But yes, certainly you can redo the analysis that we have done here and test. So in other words, as you can see, now if you actually do your coarse graining, now you're going to have even more overlap. So the particle is even softer. But certainly you're going to have But maybe as you make them softer and softer, I don't know, maybe we are going to lose completely the exotic phase, I don't know. But
Okay, so let's thank Luca once more. And we go for T, we come back